Okay, so if we try to repeat this construction here, this building for this surface, using exactly the cross section, we will run into some problems. Okay, um, so the topology of these inner curves here is identical because they come from the same surface that we obtained with the first execution of the loft. So all the three curves have 6 control points and degree 3. Okay. Um, so when we perform the loft, we will always get a degree 3 cross-section complexity with six control points. But the shape of these curves here and also their geometry, basically, when we use it inside the loft command, and we are going to select all these lines this time, by default, the loft command creates a smooth interpolation between the cross sections, so it doesn't create creases. The only way to create creases using a loft command is switching to straight sections. But switching to straight section loses the degree 3 interpolation between the cross section themselves. So if I hit OK, you see that we have this kind of surfaces. They are always, let's say, degree 3 interpolations, but creases or cross section becomes inner edges. So the result is going to be a polysurface. And this surface, I have exploded the polysurface. This surface here, if I activate the control point, is going to have only 2 control points, from the start cross section to the intermediate cross section. So the topology of this object here is absolutely not good for creating this kind of object here. So you see that is not the same to prepare the construction curves and execute the loft, rather than execute the loft with the right topology and eventually apply some topological editing in order to create this effect here. Okay, so it's not like one way is better than the other. It's just that there is no other possibility, okay, to create this kind of situation. Of course, there are other ways, but they are way more complex than this one. For example, we should consider creating something like, in order, for example, let's concentrate on the inner stripe here. So the inner stripe is a valley that runs from this crease to the valley bottom here to the other crease, the opposite crease, right? And in order to create this surface, this internal surface, with a traditional direct modeling method, we should at least count on, well, I will do this with a annotation, so there is no need to do it physically in Rhino. We should rely at least on this curve here, and then this side crease, this other side crease here, this valley line, which is going to be this one. And also, in order to maintain this kind of valley aspect along the inner part of the surface, if we, for example, take into account only these lines, as this edge is straight, and we have a flat line, even if this is curved, it lies on the horizontal frame, then there is no need for any command that you use to create this kind of valley shape. Okay, so we will also need at least one cross section, probably in the mid section of these curves, like this. But we are going to deal with 1, 2, and 3 curves in this direction, and with 1, 2, and 3 curves in the opposite direction, which leads us eventually to the only possible, well, it's not the only possible command, but we can work only with network surfaces right here. The other alternative is the patch surface, but I do not recommend to use the patch surface if you want to maintain some topological control. So the alternative here is only the network surface, which leads us to an extremely high level of complexity for the surfaces. So I don't recommend using the network surface unless you are basically performing an operation that doesn't need any additional modeling operations, okay, or editing operations, because the level of complexity is so high that it's basically way too difficult to perform any additional operation on the surface. So you see that, for example, in order to obtain the same result, we should work with polysurfaces and create each of these three surfaces here independently from the other one. Okay? So we get topological differences between the three parts of the object, which is not the same because here we have a unique object with a unique topology, which is perfectly clean and smooth. Okay, so once again, you see how working with direct topology editing, like point editing, also in case of surfaces, is more useful than creating a complex set of construction curves and operating directly with direct surface modeling. Okay. Now, as regards the loft, there is another consideration that we might want to do, and it's like it regards complexity of cross sections. We saw that sometimes like curves can become very, very complex, like in this case. Okay, so I'm going to use this example here in order to analyze, for example, the loft creation. Okay, so I'm going to take back the surface and the curve on top of it. And I'm going to perform the projection once again. So I will project this curve onto this surface and obtain this. And now I want a surface that starts from this line and connect to this line here. Okay, so these two lines have a very different topology. And eventually I also want, for example, another curve on top. So I'm going to create a more complex loft. And in order to maintain exactly the same vertical alignment, I'm just going to take the inner control points of this curve and move them vertically. So this vertical displacement is not changing the horizontal projection of this curve. If you see this from top, you see that we are not changing the horizontal behavior of the line. We are just changing it from a front view or vertical view. Okay, so these three lines basically overlap perfectly from the top perspective. Okay, so what I want to do, I want to create the loft between this curve, and this curve. Now these two curves have exactly the same topology. Okay, besides the displacement of the control points, but this one has a very complex topology because it comes from a projection. So what happens if I create a loft between this, and this? What happens, and not, of course, not with straight section, but with normal. Okay, what happens is this. Now, this is extremely problematic because the fact that the isocurves are so much depends on the fact that the lower curve has a very high level of complexity. So remember that isocurves are not lines. So what we are seeing here are the presence of an extremely high amount of spans, okay, and also an uneven subdivisions of the curve in terms of spans and knots, okay. And up we have these two curves with a lower level of complexity, but it is normal for the loft to use the higher complexity in order to represent and pass through the simplest cross section. The problem is that these two curves don't have the same complexity, don't have the same amount of control points, knots, and spans. So the common normally flows through these cross sections and adapts the spans and knots position, and therefore also the control point of the surface, the best it can in order to pass through these curves. Okay? So this generates some unwanted behavior, like, for example, I don't know if you can see it, but this is like a twisting of the surface or a side sliding of the surface. So when you see isocurves doing something like this, start to worry, because sooner or later you will have some topological problem in terms of editing or creating some further elaborations on this surface. First one, for example, would be these nice cuts that we created here that were perfectly aligned with the isocurves, because the isocurves depended on the topology that we were controlling. Now we are not controlling topology here because this is an automatic interpolation. So if we try to extract isocurve, this is the behavior that we are going to get. So if we want vertical holes or cuts, we cannot do this with by simply extracting isocurve, because they will come bent like this. Okay. So how can we solve this problem? Well, Actually, of course, we need to obtain a more regular topology. And not only a more regular topology, but also because one could say, okay, I take the lower curve and rebuild it in order to have a less complex topology. Well, actually not with 4 control points, because as we get this kind of total deformation of the curve, but eventually, I don't know, with 75, we already get a very good approximation of the curve. Eventually, with this kind of maximum deviation, I would eventually decrease the amount of control points and go back to a more acceptable compromise between the complexity and the precision. Okay, so if I rebuild this and delete the input, okay, I don't want to. Well, no, I'm not going to delete the input. So let me do something like this. I'm going to take this curve and I'm going to change its color to red. Okay, so I'm going to select it once again and rebuild it with 50 control points, and don't delete the input, and hit OK. So now we have this one, which is the regularized topology, and I'm going to change it to green. Okay, so the green line is the good one, and the red line is the old one. And we can see that there is some difference between the two. When you see this kind of flickering between the colors, it means that there is some difference between the two geometries. So this is the curve that I want to loft together with the upper curves. So loft and select the green curve, this one, and hit enter and switch to normal. You see that having a more regular topology is not enough for regularizing the vertical aspect of this isocurve. Why? Because the lower curve has a constant speed now, because the control points were redistributed in an even way along the path. The knot vector is uniform knot vector, and these two features make the speed of the curve constant. But here we have two different topologies from the lower one, and the speed is not exactly the same. So it's the speed that makes the isocurves bend along the path. Okay, you see that, for example, in the upper part of the surface, you have this kind of bending of the isocurve, but this bending depends on this part, on this different topology. But if you take a look, for example, at the start point and end point of the isocurve on the two upper sections, you see that it's more or less aligned vertically, okay? Because these two sections have the same speed. Now, in order to have three curves with the same speed, you also have to rebuild the upper sections. Now, you can do this by hand, like rebuilding with the rebuild command outside from the loft, but you can also do something different, like simplifying the cross-section curves inside the loft options. So if I rebuild the whole set of cross-section with the same amount of control points, then I am regularizing the isocurves. And it's interesting, for example, right now you see there is still some bending occurring, even if they have the same topology. But this is way less than the bending that we were getting before this kind of operation. The only problem with executing the rebuild inside the loft option is that you don't have any control on the deformation that you are getting from this rebuild. So there is no maximum deviation parameter inside the loft options window. So of course, reducing the control point from 50 to 30 for the lower curve is still deforming the curve too much. And we see that, for example, the surface is not connected to the actual cross section because it is being deformed due to the decrease of the amount of control points from 50 to 30. So there is one reason why eventually I would take these lines here and perform the same rebuild outside from the loft options. So I already have a green curve here. I also need to rebuild these two guys here. So I will perform a rebuild of both curves in order to keep under control the maximum deviation. Of course, in this case, I want to increase the amount of control points because I want a uniform topology for the three lines. Okay, and so in this case, I'm going to delete the input, so I only get the good lines. Okay, so the topology is now uniform. I perform the loft between the green curve and this one, hit enter. I don't need to simplify the cross section because they already have the same topology, right? And so I simply hit OK. Now the problem what is that I rebuilt the lower curve, not the upper curve, because I increased the amount of control points from 7 to 50. So there is absolutely no possibility that the resulting curves are way too different from the original shapes, okay? But this one has been rebuilt with half the amount of the original number of control points, okay? And therefore, the deformation was 0.007, but we are working with a tolerance of 0.001. So we obtain a deformation which is 7 times uh, more important than the lowest detail possible for Rhino. So for Rhino, this green curve no longer lies perfectly on the surface, which means that this loft doesn't touch the underlying surface perfectly, where perfectly means with a lower separation than the absolute tolerance that we have here. And so any operation that we try to do between these two surfaces is going to result in some, well, error or bad behavior. For example, if I take these two objects and try to calculate the intersection, well, actually is giving us a good result. This was quite unexpected. I was expecting a set of more open curves from this intersection. Eventually, is because there is a maximum deviation of 0.007, uh, but eventually this level of details, this level of separation happens in a very localized spot along the curve. Okay, so obtaining a maximum deviation doesn't mean that you have whole portions of your curve to have that separation. Okay, so if that value only involves a specific spot of the curves, then in that case you still have enough precision in the coincidence between this surface and this object here. Okay, but if we, for example, repeat this with less precision, so it means with less control points, then eventually from this intersection you will get separated segments for the intersection. Okay, so this could be one problem. I'm not going to repeat the loft, but you can try this if you want. You can simply decrease the amount of control point for your rebuild, and then take into account the value for the maximum deviation. But in that case, but just performing this intersection would result in separate intersection lines. Okay. So not in this case. But anyway, this is something that you might want to take take into consideration, because the precision of the cross section can be adjusted, or the rebuild of the cross section can be performed outside from the loft and inside of the loft as well. The only difference is that you don't have control over the maximum deviation, which is an important parameter. Another consideration is that, sorry, this is the rebuilt loft, okay? So this is a possibility you have. But you saw that always in the loft option window, there is also another possibility for the cross section, which is the refit. Now, rebuild and refit are two different operations that they both rebuild or simplify the curves. So they change the topology. Now, what's the use of refit? And you see that also fit was one of the options for the curve editing. Okay, refit curve to tolerance, which is actually what is happening here. Refit using this kind of tolerance. Now, the refit actually changes the shape of a curve in order for that curve to be simplified in Rhino terms within this kind of tolerance here. Okay, so let's see what, for example, what happens if I have the red curve, which was the problematic one or the projected one. Okay, so I have this red curve. Let's switch it back to black so it's more visible. And this is a problematic complexity, right? So we want to do something with it. And I don't want to rebuild it. I want to refit it right now. So I'm going to take the fit command. And the fit command says, okay, what's the fitting tolerance? And the fitting tolerance is now set to the absolute tolerance of Rhino document. Now, this is a good approach because if you say, I want to fit or refit this curve using the absolute tolerance, the topological editing that happens will respect the actual shape of the curve within the absolute tolerance of Rhino document. So for Rhino, there would be no difference between the actual curve and the refit curve. Okay. Let's also see if no, I can't. So I'm going to create a new layer, like layer 01, and give this the green color. Okay. So I'm going to take this and refit it and say output layer is going to be, oh, sorry, I have to switch to layer 1. Okay. So refit this and output layer is going to be the current layer. So the refit curve will be placed inside the layer 01. Okay, so I leave the fitting tolerance to the absolute value. I'm not going to delete the input because I want the black line to stay on default layer. Degree 3, I'm going to keep it because I don't want to change it, of course. And well, angle tolerance, we are not going to work with this right now. Just concentrate on the fitting tolerance. Okay. So if I hit enter, now I get two curves. Okay, and see the control points of this curve. They are extremely regular. Okay. So what the command did was rebuild this curve actually, but fitting the result to the original curve with a tolerance of the absolute tolerance of the document. So I know that topologically speaking, this might be the best compromise between the original weird topology and the best topology that allows to respect the absolute tolerance of our document. So for Rhino, there is absolutely no difference between the green curve and the black curve. Even if we go very, very close to this line, you see that this flickering means that the curves are somehow different. Okay, so let's see if I zoom window, for example, in these areas. Let's see if we manage to see some. Yeah, you see that there is this very, very, very small difference. This is 1 micron, basically, maximum deviation. Okay, so this is probably the best way of rebuilding a curve according to the document tolerance. Fitting doesn't take into account the even distribution of control points along the path, okay? Because it is based on fitting tolerance. Now, fitting tolerance means that the maximum deviation must be contained inside 0.001 units. And we saw this previously with Grasshopper. I showed that when the curve has more curvature, in order to maintain that tolerance, you need more control points. When the curve becomes smoother, you need less control points. So there is not an even distribution of control points along the path. You see that in this part, they are denser than in this area here. Okay, so but this is the best topology in order to maintain that tolerance. Okay, you have no control on the amount of control points. So the final result, for example, here is saying 62 control points. Okay, but for example, in order to observe this, I'm going to take the fit curve, like take it here, and take this one and eventually rebuild it with the same amount of control points, 62. Okay, so you see that the maximum deviation is higher actually than the absolute tolerance. Okay, very small difference, but this is higher than the absolute tolerance. So if I don't delete the input, I get, this is the weird topology, this is the rebuilt curve, and this is the refit curve. Okay, so there is a slight difference with that amount of control point between the shape of this curve and the original one. This is something that Rhino could detect because the maximum deviation was higher than the absolute tolerance of the document. The difference between the shape of this line and this one is undetectable for Rhino because we work within the absolute tolerance value. Okay, so any operation you perform on this topology, which is way more regular than the original one, will result in a perfect workflow or in a result that you can foresee. But when you work with this, it's like 50-50. Okay, because you are working with a value a deformation which is higher than the absolute tolerance. Okay, so I would say that this curve, for example, can absolutely be read. Okay. So take into account these two operations now, the rebuild and the refit, and let's go back to our loft. Now, despite the fact that there is a refit possibility inside the loft, I would not recommend you use it. So let's see why. If I loft the red curve, the black curve, and the black curve, these two always have the same topology, even if we rebuilt them previously with 50 control points. Now, if I do this, and I use normal and do not simplify, I start to have this kind of strange behavior. Even if the lines seem to be very good oriented in this moment, you see that there are some isocurves which are extremely close. Okay, this means that in these areas the surface has a slower speed. Okay, so you always aim to obtain the more regular topology possible, not only for the orientation of the isocurve, but also for the separation of the isocurve. If you see this kind of variable separation, it means that this surface is faster, slower, faster, very slower, somehow faster, no, and then becomes very slow here and so on. Okay, so you don't want this. And if I rebuild this, well, we already know, okay, constant separation, smooth surface, and the constant speed, and so on. Everything is perfect here. And from this point of view, I have no interest in simplifying too much the cross section, because if I simplify too much, if I reduce the amount of control point too much, the risk is that I work out of the limit of the absolute tolerance. So I prefer to increase this also to, I don't know, 100. Okay, it doesn't matter. The important thing is to have a regular topology. Okay, well, of course it matters. Okay, if there is no need to reach these higher numbers, you don't, because this is going to produce some heavier geometry, which is heavier to render, heavier to save in your files, and so on. Okay, so you might want to also think about optimizing the size of your files, of your document. But in general, this topology is the same, is as good as a simpler topology, okay? Because it has constant speed and regular isocurve orientation, okay? What happens if I use refit? The refit doesn't eliminate the problem of the difference of topology. Well, actually, it increases the problem, okay? It makes it more evident. So what you should do eventually is decrease the resolution. But if you decrease the resolution, you don't eliminate the weird behavior, because the topology of these three lines is way too different. Okay, so you will always have some kind of bending of the isocurve. And moreover, what you get is a total separation of the actual cross section from the original cross section. So you are almost surely working out of the limit of the absolute tolerance. Okay, so refitting the curves inside the loft is not recommendable in general, especially if you want to maintain some kind of geometric and topological control. Okay, so as you can see, I do not recommend to perform this operation inside the loft, but as we were discussing here, in general, this is probably the best rebuild tool that you can use in Rhino, because it takes into account the tolerance, the absolute tolerance of the document, and also tends to reorganize the control point in an intelligent, smart way. Okay, but not inside the execution of any surface creation command. Okay, so you might want to don't simplify if you already have the right topology for your cross section, or rebuild the cross section with the same topology in order to get to the smoother and nicer topological result possible. Okay, so this is the important part of the loft command, and as you can see, everything is basically determined by some topological consideration. Now, speaking of surfaces that sweeps along the cross section, there are the two sweeps commands. Now, in general, I do not recommend to work with the sweep one rail. The sweep one rail is a command that only works fine and produces a controlled result only under very particular circumstances. So, for example, if you have a clear relationship between the rail and the cross section, then everything works fine. For example, You can think of using a, let's go into the front viewport and use this rectangle. Oh, I don't need to work in the layer 01. I go back to the default layer. Let's create a rectangle. And we can use the sweep one rail to create some complex shapes with just one single execution of the command. So for example, if I take a polyline starting from the midpoint here and activate the project command, planar is already activated. So whatever thing I do here, I'm staying at the same height. Okay. So what I want to do, I go into the top viewport right now and draw around the edge of this rectangle. So I go, for example, out here and then draw this segment, and then this segment, and then start to do something, I don't know, anything. Okay, so I switch to mode arc and I try to do something like this. So I'm basically designing something like the frame of a, I don't know, picture or something like that, and then reach this point. Okay, then I take this polyline here, explode it, get rid of this line, and join it back again. So I have one closed polyline in this case, which lies at half the height of this frame. Now in this case, I can use the sweep one rail using this rail and this section, because I know that as the situation is extremely regular and controlled, what I get eventually is this perfect sweep along the sweep one, the one rail that I'm using. Now, eventually here I would do some topological consideration in terms of, is this the best topology possible for this frame? I don't think so, because the way that the sweep one rail worked creates, for example, this internal edge here at half the height of this side, because the cross section is here. So the sweep starts from here and reaches down here. So this is an internal edge, which is absolutely unnecessary. So the opposite side has only an isocurve here. So eventually I would get rid of these two surfaces here, or polysurfaces here, and eventually mirror just this one here on the other side. Okay, and the other topological problem that we have happens in the corners. Okay, because we have this edge here, which is not necessary, and also this one. Okay, so we have some surface going on here, splitting the whole side of this frame at this height, which is useless. Okay, we can avoid it. So you see that the sweep is not producing the best result possible. Eventually, you can take this edge, well, this cross section here, create some kind of a straight extrusion like this, which is higher than the edge itself, and then eventually start to mirror this 45-degree, create the upper side, mirror it, and have the lower side, and mirror this on the other hand, and have the left side, which are basically one single extrusion. They still are polysurfaces because the cross section that we are extruding is actually a polyline with vertices. Okay, so you always get a polysurface as an extrusion. Eventually, what you can do in terms of topological consideration, you can also avoid having these vertices here. Now, what would you do to eliminate these vertices? Eventually, the average user, what he or she would do would be using some fillet. Okay, so I have this section here. I see that this is 1 millimeter. So eventually, if I fillet all this corner with more or less the radius of 0.2, I would get a nice smooth aspect. Okay, so let's try and do this with a copy of this line. Okay, so I'm going to apply a fillet corners, which is this one, with a radius of 0.2, and have this nice smooth result. Okay, but this nice smooth result is producing this kind of situation here. The fillet is a constant radius curve because it is an arc, right? It's a portion of a circle. So we pass from a zero curvature segment, which is this one, straight line, to a constant curvature segment, to a zero curvature segment again. And this happens with every single fillet that we perform. Okay? So if I analyze the curvature of this line, like with a curvature graph, you see that this is what happens along this line. Okay, there is zero curvature, curvature constant, zero curvature, and so on. Okay, now I created this as a polyline with arc segments. So each time I clicked, I was ending an arc and starting a new one. So there is curvature discontinuity also in these points here. What does this mean? That if I take this curve, okay, the polyarc together with the fillets has created a unique polyline, a unique polyarc curve with curvature discontinuities all over the segments, okay? So if I extrude this line and take a look at the result, you see that each fillet becomes a surface. So we still have a polysurface. So we created a more complex result, even if we were smoothing or rounding. Well, this is not smoothing, actually. This is rounding the corners. So if we round the corners, we create a discontinuous a connection between the sides, okay? Because the fillet is a constant radius curve, okay? So how can we get rid of this discontinuity and eventually create a one unique smooth surface for as the extrusion of this line? We cannot work with a polycurve like this one. We must work with a unique curve. So if I take this, for example, and rebuild it with, I don't know, 100 control points, okay, and delete the input and hit OK, I get this line here, which is basically identical to the filleted curve that I had, okay? And this is one single smooth line. So if I extrude it, I get a more complex topology, of course, but if I explode this extrusion, I get one single surface, okay? So is this less complex than this one? Well, it depends on what type of complexity you are considering. Having one single surface instead of a polysurface is already better for modeling purposes. Okay? Having a higher level of complexity in terms of topological density might be, let's say, an increase of complexity, but we have an extremely regular topology. So in this case, eventually, I would say that this is way better than this one. Okay? So you see that always, once again, we are considering the sweep and we still go back to complexity control in terms of curves. Okay, so everything is back and forth in this topological approach to modeling. Okay, one other consideration that you might want to have for this surface here is that you see that the seam, which is this internal edge, is basically happening here on the front of your curve, basically, and surface as well. Well, eventually, this is a detail that we don't want to have it visible, even if it doesn't matter in terms of, for example, of visualization, like rendering and so on. If I render this, there is basically no visibility for this internal edge, right? So it's not a visualization problem. It's a topological problem. So having an edge which is exposed like this, well, basically means that each discontinuous behavior will happen in a visible part of your piece. Okay. So in this case, eventually, I will go into the surface tools and use the closed surface seam, which is basically this inner edge here, in order to bring it to an invisible part of your model. Like, for example, I don't know, here. Okay, so you see that I have changed the position of this internal edge, which is now here on the back of my model. Okay, which means that if I hide the isocurves, so isocurve density set to disable, I see a perfectly smooth surface without any internal edges, but this one, okay, which lies on in a position that is not disturbing any process. Okay, so you see, even in this case, sweep one rail also in this configuration needs some topological tweaking if you want to get to the easier or simplest result possible. And also in terms, not only in terms that it's not that these internal edges bother me, okay, is that this is a physical discontinuity between this surface and this one, which is absolutely useless. Okay? You can avoid it. And in order to avoid it, it's better if you work with simpler commands and with simpler topologies. Okay. Now, if you want to, let's say, get rid of this separation here, you can also tweak the result of the sweep one ray. You can avoid this kind of separation, but you cannot avoid this separation here. Now, here, for example, if I take this object here and eventually go into the solid tools and extract some surfaces, like, for example, this one, and this one, and this, no, sorry, this one, and the upper one, I can delete them. I am creating an open polysurface where the only thing that it misses is one single flat surface. So I can cap this planar hole with one surface. And you can see that I have a smooth surface from top to bottom, okay? But I cannot do this, for example, in these areas because this is not a planar hole. So I cannot cap it. So eventually I would have to extract these surfaces here, all of them, also the upper half, and also this one, get rid of them. And now, how can I rebuild this whole side for this frame with one single operation? Well, what I need to do is eventually make a surface between this section here at the bottom and the upper section, because I have straight lines here at the sides, so a loft is enough. Okay, but the problem is that as I had this kind of separation here, also in the horizontal part, this is one edge and this is another edge. So I need first to extract these two edges. Oh, and I see that I also have some internal discontinuity because of the fillets, you see? So this is a very, very bad topology. You see how many work I have to do because I preferred to not rebuild, for example, the cross-section curve for my sweep, okay? Or instead of working with an extrusion, I decided to work with a sweep. And now I have to deal with this kind of situations here, which is this one at the bottom, but also this one at the top, because I have exactly the same topology for these edges. Okay, so I have to extract one by one all these arcs here, okay, and then join them together in order to have two curves. And you see that, well, actually I'm getting 4 open curves, and this is interesting. Let's see, curve, and it doesn't join with this one. Okay, so now this is absolutely I was not expecting this. Let's go and analyze this detail. I activated the control point and selected only a few control points in order to zoom to selected object. You see? Oh, I missed this edge here. Okay, there is a smaller edge because this is a trimmed surface. Okay, so there was a trimming that splitted one single edge at this height. So I also need to extract this little edge, now that I know, also at the bottom. See how much time I am wasting because of my decision to don't work with an optimized topology. Okay, so I suppose that also here you see that I have this missing edge. Okay, so now I can select this curve, plus the edges that I just extracted. So like this and like this, and join them all together into 2 open curves. Now, I'm not going to consider it, but you might already think that the topology of these curves here is way too problematic because it is made up of a huge amount of segments. Okay, while it could be one single smooth curve with the same aspect. Okay, I'm not going to rebuild them because if I rebuild them, the surface that I'm going to create will eventually not join well with the remaining surfaces. Okay, so I'm not going to do this. But if I perform a loft right now between these 2 lines, what I get, without simplifying anything, what I get is this surface here, which is one single surface from top to bottom. And in the end, we get this kind of topological complexity, which is basically correspondent to this one, more or less. Okay, so there is no particular advantage of choosing or sticking to the sweep one rail in this case, rather than performing a different operation like the one that I was doing, rebuilding and basically extruding this new curve in order to attain a more regular topology. Okay, so you see how many problems I had in order to regularize and simplify this kind of aspect for our frame, and we still miss the upper surface, which would be a mirror of this one, and we must basically get rid of all the discontinuities that we have along the frame. Okay, basically we just need to solve this problem on one side, and then we mirror, and we have solve all the problems. But yet, this is a very time-consuming process, okay, that we would avoid it if we decided for a different workflow, okay? So see how topology can, understanding topology can also put you in the right path before starting to model, okay? So take this consideration not only as a guide for editing existing geometry, but also before creating geometry, what is the more efficient way that I can create that geometry? And normally this involves some topological consideration. That said, the sweep one rail, I told you that it's problematic not only for this situation here, but also because it's very difficult to control unless you have a very regular distribution of curves. So for example, in this case, there is no problem in understanding that if I take a rectangular rail and a cross-section like this one, which is perpendicular to the rail, I will get a regular frame. Besides the topology, I will get a regular geometry, okay? But what happens if I use, for example, a completely irregular situation, irregular construction lines? For example, a rail which is something like this, which is very common in Rhino. So it's a NURBS curve with some up and downs along the path, like this, okay? And I want to create a sweep with this unique rail of a curve which is something like this, okay? And also with some internal deformation, okay? So if I try to do this rail cross section, I start to get some strange result, okay? So for example, if I turn to shaded mode, you see that there is something weird happening along this this rail, and this behavior is the default behavior of a sweep one rail, which is called freeform, okay? Now freeform is based on another topological consideration that depends on the fact that curves or NURBS curve not only have a topology in terms of control points, not vector and degree, they also are oriented lines, okay? So being this an oriented line, it means that it flows from one point to the other, but also that when it does something like this, there is some twisting going on along the path. So freeform takes into account the eventual twisting occurring inside this, this curve. Now, this is something that in Rhino is simply invisible, and there is no possibility to see it unless you perform, once again, you perform a curvature graph analysis, and you get this curvature graph that we are going to display, okay? You see that the curvature is actually creating some kind of spiraling along this, this line, right? Because the curvature graph appears on the opposite side of the curvature circle. Now, the curvature circle, if we want to visualize this, we keep the curvature graph visible, and we can visualize, for example, conduct a curvature analysis along the path. You see that this curvature circle here is changing the orientation. Okay, so let's disable the snap here. So you see that it changes not only its radius, but also its orientation, okay? So this means that this curve is twisting, right? So orientation and twisting are basically the same aspect of one single geometrical properties in this case. It's not topological properties, but it's geometrical properties. So the fact that this curve twists along the path means that the cross-section, the sweeps normally are programmed to maintain the same relation between the cross-section and the rail. So for example, if this curve connects to the rail more or less 90 degrees, then all the sweep will maintain all the isocurves connected 90 degrees to the sweep rail. But what happens with the orientation of the curve? Now let's go once again with Grasshopper. I'm going to take the rail curve, set one curve, and that's it, okay? What I'm going to visualize right now is a thing called the perpendicular frame. This is also a parametric analysis. So I'm going to reparameterize once again and take a normalized slider and take 0. So this is actually the perpendicular frame to the starting point of our curve. Okay. Now, if I take the curve and take this control point here and move it, you see that this perpendicular frame is changing its orientation, right? So what does it mean? It means that the relationship between this curve and this line is not only the inclination between the tangent lines to these lines, right? But it also depends on the relationship between this curve here, the cross section, and the orientation of this perpendicular frame. So the perpendicular frame has its red axis pointing more or less upward, okay? Now, during the sweep, I'm going to increase the preview plane size to 10. Yeah, okay, so it's more visible, okay? Now, let's take a look at what happens if I flow this point and this frame along the curve, right? Take a look at the red axis. So if I start to move this, the red axis is still pointing in the same direction. Now it's pointing more horizontally. Now it's pointing more downward and keeps on pointing downward, okay? So remember that our curve, with respect to this axis here, is basically more than 90-degree rotated to the left, okay? So if I go to the endpoint and see that this is rotated like this, I expect my cross-section to become almost vertical here, starting from horizontal and getting almost vertical. So when I do the sweep one rail, you see that in the end, my cross-section becomes almost vertical, because what is twisting is the internal perpendicular frame, because there is an orientation and a twisting going on, okay? So it's very difficult to control a sweep one rail with a free-form style if you don't have regular configuration both of the rail and of the cross-section. So in this case, the result was totally predictable, because the rail is a straight line rectangle, okay? And the cross section was perfectly perpendicular to the rail. So the rail is not twisting because it is made up of straight lines, and the cross section is perpendicular to the rail, and it remains perpendicular to the rail. The fact that the section is perpendicular to the rail is what makes these separation edges appear in the corners of our frame, okay? But in this particular situation, you see that we get a totally uncontrollable result, because we have no control over the twisting of this curve, okay? So freeform frame style, sorry, is something that is very difficult to control in organic situation or freeform situation, okay? That's why I normally try to avoid this kind of constructions here, because they are geometrically basically uncontrollable. Of course, you can decide, for example, to use the road-like. Now, the road-like means that basically you make the sweep behave like if it was a road. And a road, for example, take a mountain road, okay? The mountain has its slope, but the orientation of the road is almost always horizontal, right? So what this road-like is saying is that the frame of the curve doesn't rotate according to the twisting, natural twisting of the curve. It remains road-like. What road-like is this thing using is basically considering the vertical direction to the actual viewport, which is the vertical Z. So if this line, this cross-section, is horizontal according to this vertical axis, it will be kept horizontal all along the sweep. So you see that this line is basically never rotating around the axis of our rail, okay? It always keeps the horizontal orientation. This is something that allows creating more regular sweeps if you want. But in terms of geometrical result, it is very, very difficult to control, for example, what happens in areas where the rails have higher values of curvature, like, for example, in this case. Now, this is something that, and you can see here what weird result we are obtaining. Okay, so this is something that we still cannot control, even if we switch to road light. Okay, now this is something that is always also a problem in a more regular situation. So, for example, what I'm going to do right now is draw a more regular rail, like this. Okay, so I have this extremely regular rail, and I have a cross section which is also extremely regular. It's just a straight line, mode line, perpendicular to the rail. Okay, so what happens if this curve has no twisting, because all the control points lie on the same plane. Okay, so it has some bending but not twisting. Okay, so if I, for example, conduct a curvature graph analysis, you see that the curvature graph is always lying on the same xy plane, so there is no twisting. Okay, what happens if I try to do this sweep one rail? What's the problem in this case? The problem is that this is the rail, this is the cross section, and in this area here, the concavity and the curvature of this rail makes this section flow. The end point connected to the rail is always connected to the rail. Okay, so it flows along the rail, but the free end point of this cross section simply follows the flowing on the curve along the rail. So let me grab a pencil here. So this is the cross section. Okay, so it is rotating because of the bending of the rail. Okay, now when we reach this point, this is the cross section. When we reach this point, the cross section is still oriented in this way because it is still perpendicular to the rail as it was at the start point of the rail, right? When we get here, the perpendicular is going to be this one. When we are here, perpendicular is this one. So in order to keep the relationship between the cross section and the rail along the sweep, this is what happens. Okay, so there is this opposite direction for the endpoint along the sweep in this area. This is a self-intersecting surface, which is something that's extremely problematic. Okay, so try to avoid this. What can we do in order to avoid this kind of situation? Well, this is one problem that depends on one general consideration, which we can observe not only with the sweep one rail, for example, like in this case. We can observe this problem here in many situations, but they all lead to one single problem, which can be analyzed using a simple offset curve. Okay, so this problem originates at the level of an offset. If I try to perform an offset curve of this thing here, you see that, let's make the through points option. Okay, so you see that the offset produces a smooth curve until a certain distance. From this certain distance on, you get this kind of intersection, right? Now, the offset is capable of doing this. It trims the intersection and leaves you with a vertex, so an internal discontinuity, a kink, basically. But it's fundamental to understand, for example, what is the maximum distance for the offset in order to get to a smooth curve. Okay. Now, in order to do this, what you must do is take the curve and conduct a curvature analysis. So right-click on this. If we do this curvature analysis, we have access to the osculating circle, which is the curvature circle. But also, we see these black dots and white dots. The black dots are inflection points. Okay, so it means that the curvature changes its sign. It goes from concavity to convexity and vice versa. Okay, and then there are the white dots. The white dots are given each one of these segments between black dots. Inside these segments, there is at least one white dot, and this white dot represents the smallest curvature inside these segments. So this white dot here is not problematic for us because we want to offset on the other side. Okay, so the only concave part of this curve on this side is this one, between this black dot and this black dot. And the smallest value of curvature, I have it here. So if I take this point with a snap and click with the mouse on it, Rhino says the radius of curvature is 6.89443. Okay? So it means that if I take into account this circle, the highest value of the offset distance is basically reaching the center of this circle. In that center, I already get a vertex. From that center on this side, I will always get an intersection and therefore a vertex. So if I consider an offset distance smaller than 6.89, I will surely get a smooth curve as an offset. So let's try and see this. If I take, for example, once again, the offset curve, and I was using 12, right? But if I take this and set it to 6 and click here, I get a curve which is smooth with a very complex set of control points, because the curve is getting with a very high value of curvature, but it's still smooth. Okay. While if I take this and make an offset of, oh, sorry, I think I have the cap activated. So cap, no. 6, okay, this is the first offset producing a smooth curve. And I'm going to offset this once again to 7 and click. Okay, so here we should have a vertex that should be this one, and here it is. It's a kink. Okay, so you see that we have perfect control over the right or problematic execution of an offset. And this is exactly what happens with the sweep. If this line, which is basically representing an offset, right? If this line measures something more than 6.9 and it measures 20.69, then it will produce a self-intersecting surface. So if I take the 6 offset, which is this one, and trim this part of the cross section and create a sweep one with this rail and this cross section, then I will get this. You see that it's not exactly the same as the offset, because there is some, well, we will see this in a while, but it's more or less identical. So if you control the curvature of the rail, you control also the needed length of the cross section in order to avoid this self-intersecting problem here. Okay. Other things that are affected by this consideration are, for example, the offset of a surface. So the offset of a surface is a little more complex because a surface has not only one curvature value, it has 2 curvature values, which are also considered in combination of the two in 2 different ways, like in terms of mean curvature and Gaussian curvature. They are 2 different meaning of the curvature analysis of a surface. We are not going to discuss this because this is very, very, very specific, and eventually you might not want to take it into account in a standard workflow. But it affects some kind of particular geometric problems, like I don't know, like something like minimal surfaces, which are a particular category of surfaces, and other particular aspects that we are not going to discuss. But anyway, you see how the sweep one rail might present some problem, and you always need some topological consideration in order for this comment to work properly. Okay. One last consideration, which has to deal with a sweep with more than one cross sections. If I go here, I'm going to keep it simple right now. So I'm going to take a straight rail, a straight cross section, and another straight cross section, like this. Okay. If I do a sweep one rail between this cross section and this cross section, you see that with free form, you see that we get this kind of surface. Of course, this is like executing a loft, actually. So if you have one initial cross section and one final cross section, and you have a straight rail, there is no need to create a sweep one rail. You can also loft the 2 opposite sides, right? But actually, there are several other comments that you might want to use. For example, there is a simple surface from 2 edges. So for example, I can take this curve and this curve, enter, and I get the same exact surface, right? So always try to use the simplest surface creation method if you have access to it. Okay, but if I take this surface and activate the control point, I see that now using the sweep one rail, I don't get a degree 3 interpolation along the path. Okay, I got the simplest possible surface, which is a four-side surface bilinear. Okay, so there is no possibility of deforming this surface internally. Okay, um, and this is curious because if the loft creates a third-degree interpolation, the sweep doesn't, and it's more complex than the loft. Okay, so this is something that I wanted to point out. Of course, if we take an intermediate cross section like this, and we create a sweep one rail with these three lines. Now it's like having three lines, three cross section with a loft. Okay, so there is no way of creating let's say a linear interpolation. Okay, so you see that now the opposite edge, which is uncontrolled, is basically treated like more or less like an interpolated curve. Well, exactly not like an interpolated curve, because if this was an interpolated curve, which is this one, this curve should start from here, point directly in this direction here, and then go and end like this. You see that there is some curvature here. That means that this cross section converts into this one, not with a constant speed. So this interpolation is slower on the first part, is faster on the center part, and slower towards the end of this interpolation, this morphing. Okay, and the same happens between this second cross section and this third one. Okay, but you can also activate the global shape blending. The global shape blending is actually considering the interpolation, the global effect of interpolating between this, and this cross section. So it is actually behaving more like a straight interpolation, like from here, I must go through this point, but then I must also, let's say, raise up once again, because the third point is up here. And so I need to prepare somehow, go lower, and then run towards this direction here. So you see that the free edge of the sweep one rail is very difficult to control, also when you have this kind of very irregular situation here. Okay, so you see that because it is always based, unless you work with only two cross section, it is always based on a degree 3 interpolation. Okay, which is very difficult to control. You can also work on curves. You see that in this case, for example, as there is the longitudinal guide, which is the rail, you can also refit the longitudinal rail. Now, in this case, as this is a straight line, refit produces no result. But refitting, you already know what it means. Okay, it has to deal with the topological fit operation. Okay, it by doing this, what you produce in your surface is a different longitudinal complexity, because refitting redistributes the control points and knots along the path, and you will get different sets of isocurves, of cross isocurves along the surface, of course, because remember that isocurves are not lines, and you have a degree 3 interpolation. So if you do this on an organic shape, you will have a different distribution of knot spans along the path. And then you can also work with cross sections, and you can rebuild them and refit them. Okay, so if you rebuild them, you will always have, well, 5 control points produce one single internal knot, so there is always the same longitudinal isocurve, but it becomes a real isocurve and not a visual one. But if you take more control points, you will have more longitudinal isocurves. Remember, you do this only if you need it. Okay, it's not because like having all these lines visible is nice visually, but if you don't need it, don't do it. Okay, by needing it means that if I get to these results, is eventually because I want to activate the control point, and I don't know, I want to take this line of control points and this line of control points and leave all the rest untouched. And so once I select these 2 points here, I can go into selection and point selection and select, for example, all the points in the U direction. Okay, so I select all the point lines. And then I go, for example, here in perspective, and I create this rebuild because I wanted to do something like this. Okay, so even in this case, topological considerations in order to get to this complex result, but with the less amount of steps possible. Okay, so you see that also the sweep one rail, if you want to work with extremely organic shapes, is way more powerful than other tools. But remember, it's very difficult to control. And one last consideration, I'm going to move this surface away, and I'm going to use this freeform curve, which has some internal knots and spans, of course. And I'm going to create a sweep one with this. And in this case, what I'm going to do, not only I'm going to rebuild the cross section, I'm also going to refit the rails, and you see the effect. Okay, so the effect is basically having a refit. When you refit something, for example, like in this case, and you have no control over the fitting tolerance, it means that the command is working using the absolute tolerance of your document, which was 0.001, 1 micron. That's why you get this kind of density of knot lines. Okay, because you have a huge amount of control points in this refitting. Okay, so for example, if I cancel this command, go into millimeters and go into unit settings and eventually set this to 1 and perform a sweep one like this with a refitting rail, you see that the refit is way less dense than the previous one because it is using the absolute tolerance from your document. Okay, so let's switch back to 0.000. Questions? Is it possible to bake the curvature graph somehow? um, no. I mean, you cannot do it this in Rhino. You can find a way of doing this in Grasshopper. So, for example, there is, well, actually, I don't remember what, but I have it. There is a component which was a script, basically, that was creating the curvature graph in terms of geometrical elements. So you had access to the graph curve, the hairs, which are all the straight lines connecting to the curve, and so on. If I am lucky, I will find it and I will share it with you guys. But I don't know. I have to double check. Yes. Okay. What do you want to do with it? It's not exactly clear, but anyway.
I mean, I think it's extremely nice, the configuration of the curvature graph.
Yeah, the aesthetics, you mean?
Yeah, exactly.
Yeah. I understand.
It was just an aesthetics thing. That's why I just wrote a quick comment.
Yeah. Okay. If I found it, I would be more than glad to share it with you guys. But I have to look for it, and it's quite. If I don't remember wrong, it's inside one very old script. So let me give me some time, and eventually I will find it. Yeah, on the other hand, there is the sweep to rail. Now, the sweep to rail is very important because it is a very powerful command. But in order to work with this sweep to rail, we must also perform some preliminary considerations. So today we are not going to discuss the sweep to rail, but we are going to take a step, I don't know if further or back, it depends on how you want to see it. But to me, it's a step forward because we are going to analyze this command here, which is the blend surface. And this is going to be heavy, okay? So take a deep breath. We have 15 minutes more or less, but I will try to be as effective as possible, okay? So what I'm going to do right now is creating two double curvature surfaces, okay? So I'm going to create a deformable plane, like here, and I'm going to copy it here on the right. And then I'm going to activate the control point of this, select them all but the surface, and use a soft move command in order to create some curvature, for example, in this area of the surface. Some curvature up, like this. And I'm going to do the same thing here, take all the control point and use the soft move command. But on this other side of the surface, I'm going to create this um, deformation downward. Okay, so I have two facing surfaces. One has this bulge upward, and one has this depression downward. Now, what I want to do, I want to create a connection between these two surfaces, right? We can do this in several ways. Okay, I'm going to do it in the more effective ways, which is by using the blend surface. Now, the blend surface is like the blend curve. Remember the blend curve that we have used to create this kind of connections between our existing curves, right? Where we could adjust the continuity level, the desired continuity level that we wanted. Now, this is exactly the same. You have blend surface. It asks for the first edge, which is this one, and it asks for the second edge, which is this one. And it creates this kind of nice connection surface. How does it work? Well, exactly like the curves. If I want position, position, I get this simply straight cross section connecting the two opposite edges. It is like using a sweep to rail, if you think about it, because you have the two rails, which are the opposite edges, and then you have this line coming out from the blend, which is basically a connection line created with the desired level of continuity. Now, if I increase tangency, tangency, I get, as a result, this kind of continuity where just two control points are involved, which define the initial tangent and the final tangent for our connection surface. Actually, what we are creating is a connection, a tangent control point all along the edges of the two existing surfaces. So you see, for example, that if I confirm this and take a look at the topology of this, you see that I have this line of control points, and then I have another line of control points here at the bottom, okay? So of course, as we are dealing with two-dimensional objects, a surface is a two-dimensional object in terms of topology. So it's a two-dimensional domain, okay? Of course, this is a three-dimensional object, right? But in terms of topology, it only has two dimensions because it has no thickness, okay? So when we work with two dimensions, like in this case, one single control point converts into a control point line, okay? It's like when we were working with kinks and kink lines, okay? Here is the same. So we have a blend surface that connects with tangency all along these two edges. Now, let's make a few considerations here because this is very, very important, okay? That's why I was saying we are taking a step forward because this comment is very complex. So the result that we get, it's a surface that is basically touching the existing two with tangency continuity. If we take, for example, a zebra analysis, this zebra analysis, oh, by the way, this is flipped. Okay, this zebra analysis tells us what level of continuity we have between the selected surfaces, okay? I'm going to adjust the mesh just with simple control in order to have a smoother aspect of our stripes, okay? So tangency continuity in terms of zebra analysis is represented by stripes that flow from one surface to another, corresponding black with black, white with white, but tangency means that there is some angle between one stripe coming from one surface and the same stripe coming from the other surface. So if you see this regular connection, black with black, but you see this break line, then it means you only have tangent continuity, okay? So as you can see, zebra analysis give you the information of the type of continuity you have, but this is visual analysis. So it might be tricky because depending on the orientation that you take, for example, like this, it seems like that the stripes flows perfectly along this connection line, but it is not. So the zebra analysis, you better move around and see if you get this kind of situation. If you get this kind of situation, at least from one point of view, then it means you don't have a higher level of continuity than the visible one, okay? So we get a connection surface with several control points in this direction, because they come from the original curve, the original plane, sorry. And on the cross section, we got 4 control points. Now, when you create a surface, like in this case, with an amount of 4 control points, let's take a look at the degree of this surface. So if I try to rebuild it, Rhino says we have 10 by 4 control points and we have 3 by 3. U3, which is basically the degree in the edges direction, depends on the degree of the original surfaces, right? But the cross-section degree, which is in this case is V, the green one, depends on the amount of control points. And the amount of control points depends on the level of continuity that we want. So if we set tangency, we need 2 control points plus 2 control points, 4 total, and we get 3 as the degree in this direction. What happens if I take, let's copy this right here. Let's get rid of this, okay? And let's repeat the blank surface between this edge and this edge. Now, let's not visualize the interior shapes. Well, no, let's consider interior shape because it gives us a smoother convection, okay? But it doesn't affect, actually. It depends only if you want to have local control over the inner part of the surface, okay? And you see that the interior shapes are set in with correspondence of each control point of your original surfaces. This is what happened, okay? But it doesn't matter in this case. The important thing is another one. So if I set, for example, curvature, tangency, okay? Now, curvature needs 1, 2, 3 control points on the edge 1 and 2 control points on edge 2, okay? So if I hit OK, I get this surface here. Now, this surface has this topology. So it has 5 control points in the cross-section direction. Let me flip it quickly. I just want to avoid the orange. I don't want to take into account the U and V direction, okay? So if I perform a zebra analysis right now on this thing here, I'm going to zebra analyze everything. So you see that now, even if I move around, it's more difficult for me to, let's say, see here that I have some kind of breaking lines, you see, on this side, because this side was connected with curvature continuity, right? So you see that the stripes always flow smoothly from one surface to the other one. While in this case, I still get this breaking line, okay? So in terms of zebra analysis, everything works perfectly, right? We were expecting this. What happens if we analyze this surface and we take a look, for example, at this degree? V is actually made up of 5 control points. But if we take at the degree, it says 4. Now, this is something that it's absolutely problematic, okay? We said that we don't want to work with degree which is higher than 3 normally, okay? And we are seeing that the blend command sets the degree according to the number of control points. That's the only thing that it can do. So when you define the amount of control points, automatically you have a degree which is equal to the amount of control point minus 1. So you can imagine what happens if I take a blank surface between this and this and set this to G4, G4, and eventually avoid some self-intersection along the way, okay, like this. So if I do this, I have an extremely continuous relation along 1 and 2, right? But I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 control points in this direction, okay? So, of course, I get perfect, smooth continuity geometric continuity between these surfaces. You see, there is absolutely no possibility that some break appears along these stripes, right? But topologically, I have a huge problem here, because if I analyze this from a topological point of view, you see that I have degree 9, okay? Now, degree 9 causes many problems, okay? Where many problems means that, for example, let's see, how can we quickly explain this? Remember that we considered these basic rules when working with control points, right? So initial tangent and interior tangency, flat portion, passage through a point, and so on, right? So here we are getting to a surface which has some higher degree. Okay, so let's take a look at what happens. Not with the surface, okay, because it's more difficult. We should conduct a zebra analysis each time that we do something. Let's do this with a curve, right? So if I take a curve and let's say I take a NURBS curve with 1, 2, 3, 4, 5, 6, 7 control points, right? And I know that if I have a curve with degree 3, I can take 3 control points and displace them and be tangent to the line that connects these 3 points, right? So if I have this line prepared with the right topology, and I want this line to reach, for example, this height, I can simply take this line, take these 3 points, and move them until they have exactly the same height of the point that I want, right? So it's easy to produce some controlled deformation with the degree 3 curves, right? What happens if I take another NURBS curve with degree, but I'm not going to use degree 9, but degree 5, okay? So I'm going to use degree 5. I know that I must provide at least 6 control points in order to maintain the degree 5, okay? So I'm going to use quite a bunch of control points. I don't even care about how many control points, right? But I have this curve, which has degree 5. And I take this control point here. Let me get rid of the gumball. So I get this control point here. I take 3 of them, and I want to move them here. Now, if I do this thing, you see that I think I am passing through this point or reaching the height of this point, but I don't. Okay? You see that the curve stops at a lower level than the level of this point. So if I draw, for example, a line from this point horizontally, I see that the control point of my curve lies exactly at the same height of this intermediate point. But the curve is not reaching this height. This is because if you have a degree 3 curve, it is enough to work with 3 control points and align them along a line to have the curve tangent to that line. But if you work with a degree 5 curve, you need to align 5 control points. And even if you align 4, you will see that there is some very small difference between these 2 lines. But if I take the 5th one, then the curve becomes tangent to the line here, exactly in the knot contained between these 5 control points. So if I, for example, try to use an insert knot command, so I can, well, let me get rid of this point here. Let me hide it. So I don't have any visible point right now. If I try to add a knot to this curve, you see that here we have a knot appearing. This is the tangency point, okay? And I had to move 5 control points in order to make this curve be tangent to this line, okay? So if you think about this in terms of surfaces, it means that you have no topological control over a degree 9 surface. The amount of control points that you will need on a degree 9 surface to produce some kind of control like this should be huge and basically uncontrollable. So that's why it's preferable to work with degree 3 surfaces. The problem is, and we are going to discuss this tomorrow as the first thing, now that we know how the blend surface and the blend curve also. So also the blend curve works like this. So if I try to blend this line with this one, and I do, for example, this adjustable curve blend between this and this, and I select G4 and G4 continuity, and take this curve and analyze this with a rebuild, you see that the actual degree is 9. Okay, so the blend, as it can only work starting from the desired level of continuity, it doesn't know what you want to do with the internal knot vector. The only thing that it can do is create a one span curve, so there is no inner knot in this curve, with a full multiplicity knot here, so 5 control point here, and another full multiplicity knot here, so other 5 control point here. So it means basically that the degree is absolutely a consequence only of the amount of control points. Okay, chat. Is it possible to have a curvature continuity between 2 surfaces still having degree 0? Yes, of course, but not with the blend surface. So the blend surface Well, think about it in this way, okay? If you try to blend surface this with this, okay, and you select tangency, tangency, you don't have curvature continuity, right? But you have, in this case, a degree 3 surface, which is what you want to get, right? So the moment you select curvature, either along 1 or along 2, or in both cases, you are increasing the degree of the surface in the cross direction. So if I do this, I will get 3 plus 2 control points, and I get a degree 4 surface. If I do this, I get a degree 5 surface because I have 3 plus 3, 6 control points, degree 5, okay? Because this is a one span curve, okay? So the degree is affected only by the amount of control points. Now, it is also true that even if you select curvature and you already have a degree 5 surface, you have curvature continuity, okay? If I select G3, I still have curvature continuity. I have more than that, but I still have curvature continuity, okay? So the blend surface and the blend curve, they don't allow controlling the degree, because they only allow controlling the geometric property, not the topological property, okay? So yes, you can still have this, but you must perform something like this. Well, let's do it at once, okay? So tomorrow we will start with another thing. You want a degree 3 surface, and then you take tangency in order to create the first version of this connection, okay? Of course, it doesn't have curvature continuity, but it is degree 3, okay? And it approximates the connection with some higher level of continuity. More than that, you can also create this blend surface dynamically, because you have access to the sections, okay? Interior shapes, with or without interior shapes, you still have tangency continuity. But the problem is that this line is basically straight, and this line has very few curvature, very small curvature. And so the tangency along line 1 and line 2 can become very local, okay? So you still are capable of seeing some kind of sudden light variation, which basically indicates the presence of a crease, even if locally, topologically, you still have tangency continuity, right? But the presence of this thing here allows to distribute one interior shape with correspondence to each control point coming from the two opposite edges, okay? So if you have this, you have access to a whole range of blend surfaces, because you can simply change the shape of one section at a time, and you can create a different blend surface, also extreme blend surfaces, like, I don't know, this kind of weavy thing here, okay? But anyway, you shape the surface as you please, because you know that you are working with a degree 3 surface, and you get the preliminary result, okay? Now you want curvature continuity. But you have a surface, degree 3, with just 4 control points in this direction. So if you want curvature continuity, for example, along edge 1, which is here on the left, you need one control point here, another control point, and also the third control point here must be used in order to create curvature continuity along edge 1. If you do this, there is no possibility that you have curvature continuity along edge 2, because you would need another 2 control points that you don't have, okay? So in order to have curvature continuity, you still must have 6 control points, but a degree 3 surface. So we created the degree 3 surfaces. We still miss the right amount of control points. So what are we going to do right now? We are going to add a knot line. We have 4 control points. We need 6 control points. So we miss 2 knot lines, okay? So if I do this, and I add a knot line, of course, in this direction, because I want another line of control points and another line of control points. So I get this, for example, and this, okay? So now I still have a degree 3 surface, but if I activate the control point, I see that I have 1, 2, 3, 4, 5, and 6, okay? So once I have this, I still have tangency continuity here and here, because I'm not changing the orientation, the direction of the first line of control points. They still are tangent, but we miss the position of the curvature control point. How can we do this? As we were doing with the match command that we were using here, there is a match for the surface. Now, I go into here, surface tool, and this is the blend, and this is the match. So what I want to do, I want to match the untrimmed surface edge to change is, here we have both edges. So when I click here, I must select not this edge, which belongs to this surface. I must select the other one, which belongs to our internal surface. So I want to match this edge with the edge of the surface to match, which is going to be the other one. And I want to match it with curvature continuity. Okay? I don't need to preserve curvature continuity on the other end because I don't have curvature continuity on the other end. So I'm not going to consider this right now. Okay? So I simply say, okay, that's it. Now I have curvature continuity along this edge. If I perform a zebra analysis between these two objects, I should see something like curvature continuity, and I don't. Well, actually, yeah, this is something very weird that's happening here because you see this kind of flickering here. This means that in this case, there is not even tangency continuity. Okay, so I did something weird right now that I don't recall. Let me double check what I did with the match, which is the only new operation that I did. Let me see if I did it correctly, right? So match surface, I want to match this edge with the opposite edge. So now I am considering curvature. You see that actually considering curvature, yeah, now it's working. So I did something weird before, I don't know what, but you see that now, for example, see this deformation here. This deformation occurs because I'm taking the third line of control points and placing them, well, he is placing them in the correct position in order to have curvature continuity along this, and this part. And of course, this is changing the shape of our surface. See what happens with these control points, okay? So this is quite a problem right now. So in this case, for example, if I don't want to affect the opposite end of the surface, yes, I must take into account to preserve the opposite continuity, okay? At least like this, okay? So this reduces the deformation of the control points, but still you see that we have this kind of weird situation. Why we have this thing here? It's because, let me take a step back. Oh, I think I undid also the insert and not thing. That's why something weird is happening. So let me recover, yeah, this thing. You see, well, what I was about to point out is that I placed a knot line very close to this edge here. So I was creating a span, very small span, another span here at the center, and a very small span here. This irregular span is actually bringing the third line of control points way too deep inside the surface. But I want, for example, this surface to be curvature continuous with this edge here in this area. So I need, for example, to add a couple of knot lines in order to have a couple of control points line close to that edge, and eventually another couple of knot lines here. So in this case, I will have 3 control points in this area, which will be used to create the curvature continuity, and 3 control points in these areas, which will be used to control the curvature continuity here. In general, I can do this because in general, the original surface tangency was already smooth enough with the edges and surfaces, okay? So in this case, what I'm going to do, I'm going to match this inner edge with this one. Oh, why I get this weird result? Oh, yeah, match edges by closest point. Yeah, okay. So yeah, in this case, this basically is due to the fact that my inner surface, let me double check this. This has this kind of orientation. So red is moving toward the right. Green and white are oriented properly, as you can see. But if I analyze this, yeah, you see that red and green are not in the same orientation. Okay, so that's why the merging was happening in a weird way. So in this case, if I don't want to reorient the surfaces, what I can do is basically tell Rhino to use simply the closest point for our command to work, not taking into account the orientation. Okay, so I can do this, and I can also, in order to be sure, match the opposite edge. You see that there is some change going on in this area, preserving the other end curvature, which is right now already a curvature continuity. And you see that now we get this surface is still degree 3, as you can see, in the B direction. And it should have, let's double check with a zebra analysis, it should have curvature continuity. Oh, we still have some artifact here. And I don't know if this depends on, no, I think this is actually a problem, a real geometric problem. This is kind of weird. I think it depends on the match. I'm doing something weird with the match. Let me see if I can do it again, like matching this with this. I want to curvature. I don't want to do an average surfaces, because if I do average surfaces, it is going to match the two surfaces together, also adjusting the shape of this one. And I don't want to lose this shape here. No, there is nothing wrong with this. Also, I'm not refining the edges, so basically these values here are not being taken into account. So you see average surface is also changing this one. No, everything is set properly. I don't understand why this is creating this kind of strange result. Also, I'm going to copy this, undo, undo, undo. Let's go back to this one, which should be tangent to tangent. Let me double check if there is something weird happening already in the blend. Oh yeah, it's the blend that is not working properly. Yeah, it's the blend in this case that it's creating this kind of problem. That's why the match is not actually working. We get a problematic situation from the blend itself. Let me double check why. So let's blend this with this once again. I selected tangency, so this should be already enough. Let's see with zebra analysis. Okay, now it's working properly. You can see that now if I move like this, you see that there is black with some breaking line here. Okay, so I don't know what I did before. Sorry about that. But in this case, for example, I would eventually add knot lines along this surface here, like a couple of knot lines like this. I'm creating a regular spans, as you can see. So we get this, and now I will match this edge with this one. Match edges by closest point, so we can simply match correspondent points, geometric points along the edges. Curvature, and then match this edge to this one with curvature as well. So eventually, now with the zebra analysis, we should get proper continuity. Well, we still have some tangency going on here now and then. Yeah, you see that there is some breaking going on still, but at least we don't have, yeah, it's very smooth on this area. But at least we don't have this kind of G0 continuity, as you can see. So this is the way that you basically adjust the continuity with the degree. So the blend tangency is not affected by the direction of the surfaces. A tangency is tangency.
The error that
Sorry.
we got from, I don't know, but you said it is a little bit strange when we are doing the zebra analysis.
Yeah,
In,
zebra analysis, I wouldn't rely on the zebra analysis
okay,
100% because
okay.
it's visual analysis. But regarding your question, the is the surface orientation important for the continuity properties of the blend? No, because tangency is a geometric condition before being a topological condition. So if you want this new surface be tangent to the adjacent one, this surface will have its control points, its line of control points created in order to keep tangency and oriented according to the direction of the surface which corresponds to the first control point of your new blend surface. So the orientation is not important in that case, but it can affect some operation, like for example in the match, as you saw, because the match tends to consider the adjacent topology. The match, for example, also has some kind of options that are based on adjacent topology. Like, for example, if you take a look at this preserved isocurve direction. Now, isocurve direction, to someone that doesn't know the real meaning of isocurve, means only, oh, okay, I want this black line to correspond to this black line. But we know that if we preserve isocurve direction, we are talking about knots, spans, and so on. Match target isocurve direction, also it depends on the actual surface isocurves or target isocurve direction, okay? So this basically depends on this basically says that you want to set the geometric property, but also taking into account the topological property of the surfaces that are involved, okay? So there are operations that depends also on topology and operations that do not depend on topology. There is one particular command that I don't know if we are going to talk about it because it's very strange, which is the patch that works in a totally free way, but suddenly it allows to adapt to exactly the same topology that you have for, let's say, an underlying surface. Eventually we were going to see this because it's the only way to control somehow the topology of a patch surface. But anyway, it's a very strange command. It's a very unlikely that you will use in your production processes. Other questions? Oh, okay. Quick off-topic question. How do you sketch in Rhino with the marker pen? Never did, never will do. You are talking about the marker pen that I was using to underline some things. It is not from Rhino. It is from the Zoom platform. So I can create annotations with this thing here. Okay, but this is not Rhino. This is the Zoom platform that allows to do this. Okay, guys, are there any? You're welcome, Jose. Are there any other questions?
I have two.
Yeah, I
Okay.
knew it.
Okay.
Oh, wait, Vito, he never asks anything. Okay, in the previous case, is it possible to, okay, what do you mean by blend or merge? What is fondere in this case? Because if you want to join them, you can do this.
I cannot read the question.
No, you don't, but I do.
Ah, okay, okay.
Oh, okay. Fondi superficie. Okay, I think this is merge surfaces. So it's this thing here. Now, yes, you can do this, but also consider that if you merge this with this, you are taking into account, for example, smooth yes, tolerance 0,001. You are not taking into account the initial topology. So, for example, you can always merge things, but you need to adjust the topology previous to this operation. Because, for example, if you have, let's say that we do things in the worst possible way. So we create, for example, a blend like from here to here with position, right? And we get this. Now, you can merge surfaces. You can still use the merge command in order to merge these two here and to merge these two here and get to one single surface. But this change of direction in this area, it's harder than this one, because here we tweaked the continuity before, the geometric continuity before merging the surfaces, while here don't. So in this case, you get always a smooth surface, but with some less smooth aspect, let's say so. While in this case, you get a perfect smooth result if you do things properly. Okay. And this is important in case you are doing this because you want to work with one single surface. This is an important step, but I do recommend that you don't get rid of the original surfaces. So always maintain at least, I do recommend that you maintain at least this and this. The inner one can be also always recreated with a blend command, but always keep these two objects here safe somewhere before merging them, because when you merge everything, you don't have access to the original surfaces, and eventually you won't be able to recreate this kind of connection. Now, this is also a very simple connection, right? So eventually, if you want this smooth aspect, there is no need to keep the history of your modeling workflow. But if you work with something more extreme, like, I don't know, blending these with these in order to create something like a wavy behavior, like, I don't know, taking this point and doing something like this and something like this. Oh, I cannot do this because this will create some self-intersection, but I can take eventually the third control point and move it away from, no, what did I do? Okay, let's reset everything. Well, this is quite complex because we have asymmetrical, anti-symmetrical surfaces. So let me do this this way, okay? So that it would be clearer. So I'm going to take the straight.
Jan, before you finish the explanation, can you repeat quick the question so we can follow?
The question was if it was still possible to merge the surfaces. And merging the surfaces gives us, as a result, one single surface, one single continuous surface instead of three separate surfaces, or one polysurface. Okay. So the goal is to have one single surface in order to perform easier topological operations. Okay. But in this case, I wanted to point out that it's important to save the inputs before merging surfaces, because if you perform some let's say complex blend operation, okay, like this, and you create some let's say complex scenarios like this one, well, this is not not so regular. If I remove the interior edges and I only add a shape like here in the midpoint, for example, like here, now I have control over one single cross section besides the initial and last cross section. So let's say I create this blend surface here, okay, which is quite complex already. And it's very difficult to recreate it, okay, unless I know exactly what I was doing. So before merging things, I would save these two before merging these surfaces, because once you merge them, okay, you get one single surface, which is perfectly continuous, smooth continuous along these connection edges, okay? So you should eventually go back and do until you get back to the original surfaces and eventually repeat the blend, okay? So I do recommend that when you merge things, you always save a copy of the original object that you are merging, okay? You're welcome. And one consideration, we are merging, but if we take into account the topology, it's important to double check that you don't have control points coincident with the isocurves, because this will mean a kink. You see that merging creates a perfect smooth connection. That was what I was saying right now. So it means that you have no internal discontinuity along these surfaces once they are merged, okay? So it means that this is one unique surface flowing in these areas. Okay, it's very important. Okay, so it means that you completely lose the original objects. Okay, once you have this kind of smooth, it's like when you extend a line. So, for example, if I have this line here, and I try to work with an extend command, you know that extension can be created with several options. If you create any extension like straight extension, arc extension, you still have the possibility to go back to the original curve. But if you use a smooth extension, I'm going to point out the position of the actual endpoint. If I extend this curve and also the position of these control points here, okay, if I extend this curve with a smooth extension like this, uh, you see that I completely lost the previous endpoint. And together with the previous endpoint, I also lost the correspondent control point. So if I do this, it's somehow like merging two surfaces. I completely lost the original input. Okay. So when you create some smooth continuous geometry, you always lose the original one. So pay attention and create a copy if you don't want to lose it. Okay. Like in this case. Now I have a copy here, so I didn't care, but you see that we have reached to a totally new object. Okay, any other questions?
I can do as last.
Yeah,
So we can just wait.
yeah. Go, Tiziano.
Okay. So basically, the first one is just something that I was thinking following the election. Like I feel that the rebuild command and rebuild not uniform and refit are quite similar on the behavior.
Yes,
Just
yes, I agree.
just because of the speed. Is the only difference the tolerance that you cannot control in the rebuild, but you can
Well,
in refit, or is something?
it's only the tolerance is like the tolerance is not important, but tolerance is very extremely important. So let's say that you have this kind of very complex shape like this, and you have two options as we saw, which is basically refit and rebuild on uniform. So if you do this, you have access to requested tolerance, and you give more or less, you say, okay, I want more or less 35 control points. Okay, more or less, well, maximum actually. And eventually the command can use less control points. And depending on the tolerance, you might or might not reach this amount of control points. And they are distributed more densely along the curve where you have more curvature. Okay. So if you, on the other hand, if you refit this, it asks only for, it asks for fitting tolerance, the degree that you want. You see that there is no control over the amount of control points. Okay, so in this case, you see that you lack some information. You see, so you have no control over the control point. So the risk is that you get a completely different topology. Now remember that the amount of control points is also important because it determines the amount of knots and the amount of spans. So if you don't control the amount of control point, the risk is that you get different set of spans between two curves. And if you want, for example, to work with a sweep to rails, you should have an equivalent topology for the two rails in order to avoid twisting of the surface and different speed along the rails. Okay, so it's important to consider the right command between rebuild, non-uniform, and the refit. It depends on the type of work and the type of workflow that you are into. If you are working, for example, with a sweep to rail, I would recommend that you rebuild non-uniform, because this gives you the possibility at least to control more or less that two different rails will receive more or less the same amount of knots and therefore of spans. Okay. While if you work with the refit, you don't know how many control points and spans you will have. Okay.
Yeah. So the difference is in between tolerance, amount control points, spans, and therefore topology.
Always.
Yeah. And the other last two questions. The first is really quick. You mentioned a type of surface that is the only surface, or I don't know if it's the only type of surface, but it depends on the degree depends on how many control points you have. What was the name of that surface?
It's a blend surface.
Okay, so it's only the blend surface that
The blend
depends.
surface,
Okay.
for how it is created, it only as it creates a single span surface as the blend curve, it only creates a single span curve. So the moment you create a single span curve, the amount of control points only affects the degree.
Okay, that was really clear. And the last, I mean, now going a bit low with the level because we spoke a lot of things really deep. If I open in Grasshopper the curve for editor, and then you go under spline, from that I understand that spline is the category that contain both NURBS, polyline, and interpolate curve, for
Well,
example.
actually, if you go here, control point curve, okay,
That's also
and
true.
but if you go here, control point curve, and
Yeah.
you are going to create a spline, right? Actually, you are going to
Yes.
create a NURBS, which is a basis spline, non-uniform and rational basis spline, okay? And if you change the degree to 1, you are
Square.
creating a polyline, which is a
Yeah.
spline.
Yeah.
Okay, so that's why you will find all the types of curves, of free-form curves, inside the spline group.
So it's correct to say that the only difference is the degree.
No,
Okay.
the differences are the degree, the amount of control point, and the
Yeah.
not
Yes.
vector.
Yeah. That's true. That's true. They are always together. These three.
They're always together. And
Yeah.
you can work with simple comments like these ones here, for example, that each time you use, for example, a NURBS curve, you are assuming that you want a uniform vector, not vector. For example, if you take the NURBS curve, you are only asked for vertices, which are control points, and degree. It automatically builds the not vector, like a uniform not vector. Okay, if you want to work with the not vector, there is the other NURBS curve command, which is the PW key, which asks for control points and not vector. Okay, the degree is automatically set to 3 because this is the default degree, of course.
And the interpolate one, it can only generate polyline, right?
The interpolate is this one?
Yes.
No, this generates a smooth curve. If you give degree 3, it generates the degree.
That's true.
Yeah.
That's true. Yeah. Okay. Yeah. So that's it for now. I think I asked.
Okay. Don't worry. Questions are more than welcome, guys.